All right, today we are going to be discussing the scientific method and different scientific methods. So, hopefully, you have your printout notes ready to go, and we can get through this as quickly and painlessly as possible. So, let's get going. So, first off, you're sitting in a science class. So, the question is, what is science? Well, according to Google's dictionary, science is the intellectual and practical activity encompassing the systematic study of the structure and behavior of the physical and natural world through observation and experiment. What? All right, let's break that down. So, the intellectual and practical. That means it involves both our thoughtful and our thoughtful reasoning and our physical actions. So it's not just daydreaming and stuff, but actual reasoning, logical processing of information, and physical actions, intellectual and practical. Okay? And it says systematic study. Systematic means that there's a process to it. So there is a system, an order to things. So systematic study means there's a process to determining what we know. We call that the scientific process. But we're not just going about things haphazardly. We're actually having a way of doing things, a systematic process. We do this and this and this and this to make sure that we know what we want to know and find out what we want to find out. Now, structure and behavior of the physical and natural world. The key here is physical and natural world. Science can only answer the physical. Science cannot answer anything that's metaphysical or spiritual or whatever. It can only answer the physical questions of the world. That's just the nature of science and what it is. And it's through observation and experiment. Without the experiment, we don't have science. We look at things, we test our ideas about them, and those processes are referred to as the scientific processes. So you've probably often heard scientific method, but there's more than one possible way of doing it. So I don't like calling it scientific method, maybe scientific methods, but I prefer to call it a scientific process because a process is just a way of doing something, not really a step-by-step thing. And the scientific method does have portions and does have steps, but we don't always do them all in order. So scientific methods, I just said this, there's not just one scientific method, but there are many. Basically, as long as you're doing all of this stuff, you're going to have all of these parts in it, and it would be considered scientific. However, you're not necessarily going to do them in the order, like step 1, do this, step 2, do this, step 3, do this. Now, there is a more common scientific method. That's probably what you were taught in elementary school and middle school, as you're going to do this, and then this, and then this, and then this, and then this. And that's your scientific method. And most of the time it does follow in that order, but not always. So the first step of the scientific method that we're going to discuss, and pretty much regardless of which method you choose, which scientific process you undergo, you're going to follow, start off by this, because it all starts with observation. We look at the world around us and we ask ourselves, okay, why does it do that? Why does it do that? I mean, if you've ever been around a 4-year-old, you get the question why about 1 billion times a day. I know I have 6 kids and I get this all the time. Why? Because they see something happen and they want to know why. That's basically what science is. You observe something in the natural world and you gather information using your senses. So you can touch something, you can smell something, you can see something, you can taste something, you can hear something happen. So using your senses, you're going to observe the world around you. Observations can be either qualitative or quantitative. These are 2 words that you probably have not used a whole lot in your life. We're going to use them quite a bit. So qualitative observations include information that describes physical characteristics like color, size, shape. It talks about the quality of something. Is it hard? Is it big? Is it small? It's talking about the quality, but it's not an exact thing. Like my shirt is blue. My shirt is a large. My glasses are see-through. Those are qualitative observations. All right. The air is cold. The sun is bright. Qualitative observations. They talk about the quality of something. And that's what makes something a qualitative. Qualitative. All right. Quantitative observations involve numerical measurements such as weight, mass, temperature. So I weigh 220 pounds. It's currently 72 degrees in the room I'm sitting in. They're quantitative measurements, quantitative observations require measurements. You're talking about an actual quantity of something, not a quality. You're talking about the quantity. So I could say something is big. That's a qualitative observation. I could say something is 300 feet tall. That's a quantitative. So big is qualitative. It talks about the quality of something. 300 feet is quantitative. It gives you a quantity. So there you go. After we've made our observations, you're generally going to ask something about it. All right. You make observations and it leads you to a question that you want to answer. Back to the 4-year-old thing. When you see something happen, you want to know why. Why does that happen? Why does this float and this does not? Why? Your question is usually why, blah, 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 blah. All right. Or if I do this, what's going to happen? These are the observations that you make and you want to know why. That's the curiosity. That's scientific curiosity right there, wanting to know why and then looking for the answer. So we come to hypothesis, and I'm going to step on some toes by saying that you have been told this the wrong way most of your life, most likely. So once a question or problem is established, you've made your observations, you've decided what it is that you want to know, you're usually going to use more observations or observations that you've already made and any other relevant information, past experiences or anything that you have, and you're going to form a testable statement. That's the key here. Testable statement that answers the question. Good hypotheses are usually written as an if-then statement. If blah, 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 then blah, 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 blah. So I walk outside. I observe the sidewalk is wet. I wonder why the sidewalk is wet. Well, normally when the sidewalk is wet, it's because it rained. So if the sidewalk is wet, then it must have rained. That would be a hypothesis. Now, I could test that somehow. That would be a difficult one to do. So I'm just thinking off the top of my head here. But a hypothesis is not an educated guess. I don't like that definition of a hypothesis because it leaves stuff out. An educated guess is saying, well, I'm going to guess about something. I think I could know that you guys are, teenagers and you are of a certain age. So I can make a educated guess based off of my years of experience in dealing with teenagers about what you do on the weekends. I could make an educated guess, but that isn't really a hypothesis. A hypothesis is a testable answer to the question that you have. And that's the key. A hypothesis has to be testable. If it's not testable, it's not a scientific hypothesis. It's just a guess. After you have your hypothesis, you're going to test it because it has to be a testable statement. So then you're going to actually test your hypothesis. And that's what we call experimentation. Experimentation is the testing of our hypothesis. The strength of the scientific process comes from testing your hypothesis. Without experimentation, science is not science. So I get in a lot of trouble with some of my friends and colleagues whenever I say that a theoretical physicist is not a scientist because they don't ever actually test anything. A experimental physicist is a scientist because they actually test their hypotheses. So if you're fans of the show Big Bang Theory, Sheldon is not an actual scientist. He's a theoretical physicist. He's not an actual scientist because he doesn't test his hypotheses. He just works out math equations. Leonard, on the other hand, is a experimental physicist. Therefore, he actually experiments, and so he is an actual scientist. So just, saying, if it's not testable, if you're not doing experimentation, you're not doing science. So an experiment is a set of controlled observations. So your hypothesis is based on observations. So now we're going to test it by controlling how we observe things. That's what we mean by controlled observations. We're going to purposely do things so that we can observe what happens. So we're going to control the situation as much as we can and then make observations of what happens. And from that, we're going to either verify our hypothesis or we're going to show that our hypothesis was wrong. Maybe our reasoned answer that we came up with was not very well reasoned, and so it wasn't right. And so we will go back. All right. So in your experiment, you're going to try and isolate one variable at a time. There may be multiple variables. So you're going to change one thing at a time. All right. So I just recently moved to a different house. And so I'm trying to figure out, okay, what's the fastest, most efficient way to get from my house to school now that I live in a different place? So I could try a different route every single day at different times of day and time what I do, but that's not necessarily a good experiment. So if I want to change one variable at a time, what I'm going to do is leave my house at the same time every single day so that generally traffic is about the same. I'm going to drive the exact same route every single day as best as I can. And I'm going to time the amount of time it takes me, and I'm going to do multiple trials there. And then after I've done multiple trials of that, I will continue to leave at the same time every single day, but I will take a different route. So I change one variable. I don't change the time of day that I'm driving. I change the route that I take. And I time how long it would take me because I'm looking for what's the fastest way to do it. And I can do that for multiple routes and find that. So I change one variable at a time. Then if I want to see, okay, what's the most efficient regardless of time of day, once I find the most efficient route, I can then, or the fastest route, I can then take that route and keep that route the same and travel at different times of day to test it. So we change one variable at a time. And by changing that one variable, you can see the effects on the other variables. So my little example, by changing which route I take, I see the effect on how long it takes me to do it. So the amount of time it takes. Okay. So we change one variable. If you change multiple variables, then you don't know which variable it is that you're messing with or that's making the difference. So you change one variable at a time, and that is going to give you the best scientific results. So good scientific experimentation takes lots of trials and takes time. So if you ever watch the Mythbusters back in the day, they used to do this really well in that they would isolate one thing and they would just try and change one variable at a time. Sometimes they did not very good science, but they would change things up. And yeah, I love that show. Anyway, the variable we plan to change is known as the independent variable. So in my example, what was I changing? I was changing the route that I take to school. So that is my independent variable. It is not dependent on any other variable. It is independent of the other variables. So I'm going to change that variable. So the independent variable is the variable that we change. And typically when we graph our results, we'll get into this later, when we graph our results, the independent variable is going to go on the x-axis of your graph. The variable that you observe is known as the dependent variable. So we change one variable and we look to see what happens to the other variable. So as I change the route that I take, I observe what happens to the time that it takes. That's my dependent variable because the time it takes is dependent upon the route that I take. So that is the dependent variable. And on a graph, when we graph our results, the dependent variable is usually the y. So we have the independent variable on the x and the dependent variable on the y-axis. A good experiment will also usually include a control. Okay, that's a variable that does not change throughout the experiment to link them all together. It's a standard for comparison. So oftentimes, if you want to see, okay, what's the best way to dissolve something in a liquid? So we're going to dissolve sugar in tea. All right, what's the best way to do it? Well, taking a glass of tea and adding sugar to it, that is your standard. Now, if you heat it up or cool it down, that would be the variables that you're changing. But your standard is what you're going to compare it against. So in my little example of driving, the control could be considered the time of day. It's the one variable that does not change as I change my routes. Okay, that's my standard for comparison, is the time of day. Now, throughout the analysis of your data, so once you've done the experiment, you've collected all of your data, then you're going to look at it and see what it tells you, what trends you might have. How do these things actually relate to each other? Through that analysis in the experiment, scientists are going to determine if your hypothesis is correct or supported by the data, or if it needs to be redefined or discarded. So if I started out by saying, I think that the most direct route is going to be the fastest route, and then I go through all of my data of all my trials, and I find out that, well, actually a longer route was faster because there was less traffic, not throughout my experiment, I find out that this longer route is actually a faster route, then I would say, well, my hypothesis that the most direct route is correct or is fastest was not correct. So I would revise it, or I would throw out my hypothesis and start over. So we look at our experiment and we ask ourselves, does the data support my hypothesis, or does the data discard my hypothesis? And then we repeat it again and again and again. We do the experiment multiple times. One experiment is usually not enough to confirm it. If you only do one trial of something, you may confirm your hypothesis, but that's not actually what happens. If you confirm your hypothesis with one experiment, but maybe something was wrong, maybe there was something that was a little bit off about some of your data, or whatever. So we always do it multiple times. And if your hypothesis does need revision, then you revise it and you do the entire process again. You design another experiment to test your new hypothesis, and you keep going. And you keep going until you have a full hypothesis that is fully supported by your experimental results. So science actually takes a long time to do something. So that's why, especially now, you'll notice since February, whenever we had our first case of coronavirus here in the United States, all the information you keep getting about coronavirus has changed what seems like almost daily, because as we learn more, as we do more experiments, as we do more tests, as we do more trials, we learn more information, so we revise our hypothesis. We don't have a current fully fledged out understanding of coronavirus right now at the time of this recording, and that's because we have not fully fledged out all of our hypotheses. And here we are at 7 or 8 months later, and we still don't know everything because we're still testing and still testing. Science takes time to do good science. Now, once you have done that, you can get to theories and laws. And there's some misunderstanding about what a scientific theory is. Some people say, oh, well, that's just a theory. Yeah, okay. Well, a scientific theory is an explanation of a natural phenomenon that's based on many observations and experiments over time. So a scientific theory has been tested. It's a hypothesis that has been tested and has been verified many, many, many times. Theories are generally broad in their scope and are made up of many different hypotheses. So they're not just like one single hypothesis. It's usually a broad range of hypotheses that all fit into one category that we call scientific theories. So there's lots of different stuff in there, and they have been tested. It's not that somebody just came up with something and wrote it down. A true scientific theory has been tested and verified as best as we can. All right. Scientific theories are always subject to change, though, because as we get new technologies, then there's new ways to test things. In fact, there were portions of Einstein's theory that were not actually able to be verified until closer to modern times, because in order to test what he had, we did not have the technology, which also leads to why there was such a technological explosion for a large portion of the 20th century, is because scientists had all these ideas and hypotheses, and so the technology innovators and inventors started to say, okay, well, let's try and see if we can figure out a way to test that. And so a lot of this new technology came about because they were trying to test theories, test hypotheses, and come up with ways to, in experiments, to test them. In fact, the internet exists so that it was created so that they could analyze all the data from the CERN super collider as they were trying to figure out how atoms were put together. It created all this huge amounts of data, so they decided to figure out some way to link up a bunch of computers so they could do better, faster, more efficient computer processing. Oh, and it had the added benefit of they could give their data and information around the world and have lots of scientists analyze it instead of just one, and so it was a whole lot better. So the internet exists because we wanted to know how atoms were put together. So you're welcome. So scientists consider theories to be fact. So if you're talking to a scientist and you say, well, that's just a theory, and they'll be, yeah, exactly, it's a theory. They consider scientists to be fact. Fact is not truth necessarily, but they consider it to be fact, which means it is the best explanation that we have at the moment. Okay, that's the key phrase here, at the moment. There's always the possibility that our science could be wrong. Okay. Excuse me. So at the moment, with the current technology, our current experimentation, a scientific theory is the best explanation we have, so we consider it to be fact as of right now. A good scientist will always consider the possibility that our theories are wrong and they could be overhauled in the future as we get better technology. A lot of what Isaac Newton discovered about the world was considered to be absolutely factually true until Einstein's theories started to be tested, and Newton's stuff is still true in a certain area. But if you go outside of that, then we have to talk about how Newton's explanations of physics and stuff don't actually fit and don't actually work when you're dealing with very small things moving really, really fast. So they had to revise that. That's the way theories work. Theories get revised. Now, scientific law is an explanation of a relationship in nature that is very narrow in scope. Okay. So laws have been tested and verified by many experiments and have never been found to have exceptions. So when someone says, well, that's a violation of the law, blah, 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 blah. No, if you take into account all of the conditions that the law states, then it's true. So it holds true every single time and has never been found to have an exception. The second law of thermodynamics says in a closed, isolated system, the entropy will always increase. Now, this is not a physics class, so I'm not going to get into all that means, but it's a very narrow thing. In a closed, isolated system, this does this. That is always true. Now, people use, well, that violates the law of the second law of thermodynamics. So you hear people say that a lot about various things, but the situation they're talking about is not a closed, isolated system. So if it's not a closed, isolated system, then you're not even dealing with the second law of thermodynamics. So a scientific law is very narrow. It's very, only in this situation does this happen. And this will do this. That's the way laws are worded. That's the way laws work. All right. Scientists do not try to disprove laws. Rather, we sometimes seek to explain why those relationships exist. So we've observed billions of times that a rock will fall when you drop it. So the whole purpose of a lot of science is to explain why. Why does it do that? Okay, let's experiment and see why. We know that this is what happens. Now, why? So laws are the things that we absolutely know, and then science seeks to think why. All right, so that is the scientific method. Those are our notes, and I hope you have a good day.